Oh, all right. Hey guys, anybody hear me? Okay.
Yep.
Oh, I'm watching the number of participants climb. People are checking in. All right. Eric, welcome, or welcome back. Okay, so welcome. I hope you guys are well. We get regular updates from the central administration about how the university is doing and how the students are doing. I have not yet gotten any indication that any students have fallen ill to this new virus, but I have learned of a bunch of students that are in, let's just say, tricky situations because they've had to care for some elderly relatives, or they've had to go overseas or whatever. So I'm not sure how many people will be able to join us today. Let me reiterate that at least for this week, I am planning to have our class at the regular time. We're just going to do it by Zoom instead of being together in the classroom. I will be recording, at least I hope I'm recording, yes. I'll record these things and I'll put them up. I've created a little YouTube channel for this semester. I'll send you guys the link if I can succeed in getting these videos loaded up there. They're big files, I'll tell you that. So the option of saving these recordings to Zoom or to Canvas, in principle, those are options, but they give us very little storage space. So it seems like doing it to YouTube is about the only reasonable place to put these things. So the videos will be there. I'm hoping that it's worthwhile for you guys to meet live like this. If so, I'll continue to do this. If not, I can just record the lectures that I wanted to give you and stick them on YouTube, and you can just, watch them at your leisure. But we'll see. We'll just let this first week go as originally planned, and then reevaluate and see what's going on. I set Zoom up so that when you guys all check in, you come in muted by default. You can unmute yourselves. At least on my screen, there's a little icon on the lower left that I can use to mute or unmute myself. For if you have something short to say, you can just hold the space bar down, and that would allow your microphone to go live. Just like in our regular classes, if you guys just want to ask a quick question and you just talk, that would be fine. If you have something longer to say, you might want to raise your hand. The way to do that, if you haven't figured it out, is if you open up the list of participants, then underneath that is a whole bunch of little icons, one of which is for raising your hand. And that would alert me to the fact that you have something that needs to be, you think everyone needs to address it. Well, so here we go. Somebody wants to raise their hand. Keenan, go ahead. Keenan, if you're saying something, I can't hear you. Oh, wait, let's see. I have to unmute you, maybe. There. Does that work? Keenan heard?
Keenan said it was a mistake.
Maybe I'm not getting any audio. Nate, I see your face. Are you saying something? You look muted as well.
Yeah, Keenan, I think Keenan accidentally touched the raise hand icon.
All right, we have a problem because I'm not getting any sound. Can you guys hear me? All right, can you guys hear each other? Nate, say something and see if anybody else.
Can y'all hear
You
me?
guys hear each other?
Yep.
Okay, what's wrong with mine?
Yeah, I think Keenan accidentally touched the raise hand icon.
Aye, aye.
Hang on. Here, I took my headphones out. Let's try that again. Nate, you want to say something again?
That's all I wanted to say. I think Keenan touched the raise hand icon by accident. He said it was a mistake. He posted it in the chat. I was just using Zoom a few minutes ago and it was working, and now I'm not getting any sound from you guys. You're telling me that you can hear each other, which is great. For some reason, I'm not getting it. If anybody has any suggestions, maybe you should put something in the chat bar so I can, my computer volume is on. Is the sound up on your computer? Yeah, I'm at 100%. Right audio device. I had the headphones plugged in and that didn't work, and I unplugged them and that's not working either. Let me try again with my headphones. All right, somebody say something again. Let's see if this is working now. Oh, I just heard a chime somewhere. Is that from my own computer?
Hello, Dr. Usin.
Ah, okay, I heard somebody. Okay, sounds like I have sound now too. Wow, that's weird. I don't know what happened. All right, so let's go back a few minutes. Somebody had their hand raised and wanted to say something. Keenan, you want to tell us what you were saying?
He said it was a mistake. Like he clicked it, just
okay.
a mistake.
Okay, there. I lowered his hand for him. And Nate, did you have a question or a comment?
I was just going to say the same thing that Yan Lin said.
Oh, okay. Okay, awesome. So at least on my end, it seems to be working now. I have no idea what just changed, but at least it's working. So yes, Yan Lin is present, and she's more of a pro on the technology than I am. So the way it's going to work is I'm asking her to monitor the chat. I know you guys like to type in stuff on the chat. So I won't be able to see that. She will be trying to answer your questions if she can, and then if there's something that she thinks I need to answer, then she will raise her hand, and I'll put her on, and then she'll kind of transmit the problems to me. Anytime that you guys want to raise your hand, by all means do it. If you just have a quick comment, like if something has gone off the view, then you can just yell that out real fast. All right. Has anybody else had any other trouble with Zoom that you want to ask the rest of the class to help you with? Obviously, you guys are the ones who succeeded in making it work. The ones who are having trouble are still not with us, so I don't know. I don't know what to do for them. Let me tell you that I am recording this Zoom meeting, and then I will put it up on YouTube. That will mean that if you share your screen or make your own face go live, that means that you'll be part of the recording. At least I think that's the way it works. So if you have privacy concerns or something, then take that into account. Maybe just use the chat, because the chat bar will not be saved. The YouTube channel is, I think it's like hidden somehow, so you guys will be able to find it, but it's not the kind of thing that a random person would stumble on. All right, that's for Zoom. The next piece of technology that we're introducing is this Piazza. You guys should have gotten an invitation somehow to sign up for Piazza. That's going to be your mechanism to get the questions answered, the ones that you would ordinarily be addressing to Yan Lin in the discussion sections. The TAs, the department somehow decided that that's not what the TAs are going to do anymore. They're not going to hold the discussion sections for the rest of the semester. So instead, they will be monitoring on, I don't know, some schedule maybe. They'll be monitoring and participating in the Piazza sections to try to get your questions answered that way. Of course, you're all welcome and encouraged to answer each other's questions. I think that it helps people to try to help someone else. As you try to explain something, it'll make it, you'll be learning yourself as well as helping somebody else. So check that out. I guess you'll need to start using that. You do have the old homework, the leftover homework that's still due Tuesday night, tomorrow night. And I'll have a new homework out for you later today that'll be due on next Tuesday. The homeworks will be able to continue on the regular basis. So Quest is still an extant part of our course, and the scheduling will be the same on that. I'll try to get the questions out on a Monday or Tuesday, and they'll be due the following Tuesday night. It will be to your advantage to figure out the Piazza and Zoom before crunch time, because at some point later in the semester when you're actually preparing for a test or something, then you might need help, and that's when you're going to need to know how to use this stuff. It's the same thing for office hours. I will still have my office hours at the regular time, but you'll need to use Zoom to reach me, and so you've got to figure it out by then. To reach me in office hours, you need that Zoom invitation. I've put an invitation for this week's office hours into the syllabus for the course. So if you go to the math department web pages, I have now changed the syllabus to the revised syllabus for for this COVID situation. So you'll see that there's a bunch of sections in there marked as an update because I've had to change things around. And that includes a link for the office hours, at least for this week. I haven't yet figured out how to have a standing meeting, a Zoom meeting that meets every Monday, Wednesday, and Friday. Zoom lets me do it every other day, but that's not the same thing except on a week-to-week basis. So I'm still trying to figure that one out. All right, does anybody have any other questions about the technology end of this? Okay, let me say something about the grading end. So we've already had a midterm exam. We will have another midterm exam, but I guess what we're going to do is, I think I set it up so that it's going to be just purely Quest-based. It'll just have to be multiple choice for exam number 2. I understand that a bunch of you guys will be in different time zones. In fact, is there anybody logging in right now from another country? I've had some students tell me they were going to have to leave the US. I guess I don't know where you are physically. Nariman, where are you? You're raising your hand.
Oman.
You're in Oman. Okay, you win the prize for the furthest away, I think. So what time is it for you right now?
It's 9, I think it's 9:40
PM, yeah.
Yeah.
Yeah, so the people who have it worst, I guess, would be probably China. They're exactly 12-hour time zones away. So anyway, here, Nariman, your hand is still up. Did you? Here, I lowered your hand for you. Anyway, so I know that that's inconvenient for people to meet at different time zones, but as long as we're doing this synchronous classroom meeting, that's what you're going to have to put up with. But that's what the recordings will be for, is that if you decide you don't want to or cannot meet us at the regular time, then just find the recorded videos later. Anyway, as far as the test goes, especially for people who are far away. I know the regular timetable might not work out well, so I'm going to set things up so that there will be a 24-hour window when you can do the exam on Quest. I think I can figure out how to get Quest to allow you like 1 hour after you start, but you can start at any time. I am going to have to ask you not to consult any other living beings to get help on the test. I just got to trust you guys at this point. You're supposed to be adults. You're supposed to be here because you want to learn something. In fact, let me say something else about the grades. As I understand it, the dean's office has now moved the deadline for declaring a class pass-fail to after the grades have already been turned in, the semester grades have been turned in, which it seems to me what that means is if you get any grade that you didn't want, you can just turn that grade into a P for passing. And the deans are now using a P to satisfy any graduation requirement that says you have to take this course with a grade of something or higher in order to be able to do something else. So it seems to me you can have, if you get any grade you don't like, just change it into a P, with the exception of if you are failing, then it's still an F, but they've also extended the Q drop date, and Q drops for this semester won't count as part of the limit on the number of Q drops. So if you think that you are in danger of failing around May 8th, which I think is the deadline for the Q drop declarations, just have a conversation with me and I'll let you know how close you are, and you could decide to Q drop at the very last minute. So basically, there's no reason for you guys to be concerned about grades. I'm still going to have the second midterm exam, and we'll still have a final exam, because I think that it'll help you feel like there's a timetable that you need to keep. Same thing with the homeworks. And it's a chance for me to give you some feedback, because, like, you know, you might want to learn just how close you are to really understanding what's going on. But come here for the learning, and don't stress about the grades. That's usually true for any course in college, but it's more true than ever for this semester. So take advantage of that to really just learn the material, and don't sweat the grades. For the final exam, I'm going to see if there's some way that I can include some free response. I know a lot of you have expressed that you actually prefer the free response. It's an administrative headache to get you guys to scan in your handwritten work and then submit that, and I have to download it and so on. But we'll see if we can do something like that. I think it is too much of an inconvenience to ask Yan Lin to do it. The TAs shouldn't be doing that for the quizzes. So as of this moment, there should be no more quizzes. I think your semester quiz grade is just going to be the highest, I think the highest 5 of the ones that you've had so far. Have you had 6 quizzes so far? Is that correct? So we'll just drop your lowest one and take the average of the ones that are left. If there's anybody who feels like their quiz grade is too low and you were really counting on the second half of the semester to pull it up, just let me know and we can create a quiz just for you and give you another chance to get another quiz grade in, see if that'll help. So, like I say, the homeworks will just go smoothly as normal. The quizzes are basically done. We'll have another midterm, but that'll be, I think, just all multiple choice on Quest. And the final will be maybe the same thing, or at least mostly multiple choice. Office hours will be by Zoom, and these classes will be live by Zoom, at least for the rest of this week, and then they'll be asynchronously available. I think that's the phrase. You can have them anytime you want on YouTube. So, does anybody have any questions then on the running of the course? Okay. Yeah, some hands. Yeah, Nate.
Just to clarify, did you say that discussion sections would be run primarily through Piazza?
Right. There's no more Tuesday, Thursday meetings. That's completely wiped off the schedule. So Piazza becomes your way to get help from the TA. And I do have to warn you that I believe the way that Piazza has been set up is that all the sections of Math 427L are together. So that's good in a way because you can ask a question and maybe somebody from the other sections can help you out. It does allow for the possibility of some confusion. If you have a question that's specific to our class, then you need to use the little hashtags that are available. They're called folders in Piazza. But you'll need to, I think there must be, if there's not already one there, you should add a hashtag that says Russin just so you can limit your comments to my sections if that seems to be necessary. Rodrigo, you have a question?
Yeah. Are you going to change the grading weight for exams, quizzes, homeworks?
I had not planned to. Should I? I mean, what sections what portions of the grade do you think should be weighted more heavily or less heavily?
Well, depending on how the first midterm is going to be structured, the midterm, I don't know if you see the second midterm being weighed less or more, depending on how many questions you put on.
I mean, I guess I could see reasons to go both ways, but probably the default is I would just stay with the two midterms are counted equally, and they're given under different circumstances just because of the situation.
Okay.
So, if you know, let me just make a general statement here. I know that some students are in a trickier situation than others. I've had people tell me with concern about they have childcare issues that they didn't used to have because now they're stuck at home and their spouse has to go off to work and so on. If you feel that the situation is affecting you in a way that's different from any other student, let me know. And there's a mechanism within the university for treating. We already have a system for students with various special needs. If you're blind or deaf or whatever, we work around that, and I will work around any circumstances that you guys bring to my attention as well. So if you need some kind of accommodation, let me know. This semester more than any other, if there's some way that you think I need to know something, then let me know and I'll try to work with you. I'm trained as a mathematician, so I for sure can help you with the math. I'm not really trained as a counselor or anything, so I can't really help you work through any kinds of like a stress issue that you might have, but I can point you to the resources and I can certainly make allowances within our class. So I'll try to help you however I can. Okay, well, you want to talk about some math? So you do have a homework set that's out there. And since you won't be meeting with the TA tomorrow, you want to ask me any questions about the current homework assignment? Okay, well, if not, let me tell you that we have another homework that I will put up that'll be due next Tuesday, a week from tomorrow. And let's start talking about the material that's on that. So just to bring you back up to speed, when we last left our heroes, we were talking about all those vector fields in chapter 4. Oh wait, I got a hand going up here. Yes, Sohaib Khan.
Yeah, I just have a question on one of the question works.
Yeah, sure.
So it was about one of the questions asked, but if R of x is equal to the magnitude of x, what will be the divergence of R, the product of R f, given for all vector fields? For all vector fields f. Yeah, I just had a particular quote.
Yeah, okay, so,
question.
All right, so here, let me show you, because I usually work on a desktop machine which had no webcam. So the department bought me a webcam, and I rigged up an old table lamp so I could swing it around. There, and now I made my own little document camera. How's that? Is that visible for you guys?
Yeah.
All right. Oops, try to get the right angle and everything. There we go. Okay. So I wrote it badly here, but this is, so they give you this function, r of x just measures the magnitude of a vector x. And then they say, suppose that you have any other function defined on Rn. Am I doing this right? So this is a vector field. That's probably capital F. Did they use a capital F because it was a vector field?
Yeah.
Okay. So then they ask you about this new vector field R times capital F. So just so we're clear on this, if you go to any point in Rn, any vector in Rn, you are already able to evaluate this vector field F to get a vector in Rn. R, on the other hand, turns that vector in Rn into a number, and now they're asking you to multiply that number times this vector. So that's scalar multiplication in here. All right, so, and then this is a new vector field. I'll use this notation. And they're asking you about the divergence of this vector field. So they're asking you about the divergence of R times capital F. Yeah? Is that the right?
Yes.
All right. So let me just remind you of this table. I don't remember what page it was on in your book. Is it this one? Yeah. So you have a bunch of the things that I called product rules. We worked through a few of these before the semester got interrupted. Oh, you can't really see these. Well, it's on page 255. I don't know if you guys managed to bring your books home with you before you left for the semester. But here's a product rule that applies to this case. If you want to have the divergence of a scalar function times a vector field, it is what you would expect out of a product rule. It's the first times the derivative of the second plus the second times the derivative of the first. Only the word derivative and times has to be interpreted a little bit differently. When I say derivative of the scalar function, that's gradient. And when I say times, that in this case means it's the dot product. So that's what you would want here. If you think about this as informally, you think about this as asking you for the derivative of this product, then you know what the product rule would ask you to do. It would be the derivative of the first times the second plus the first times the derivative of the second. But more precisely, that's sort of informally. More precisely, what that means in our case is it's the gradient of R dotted with F plus R times the divergence of F. So there's not really much to say here because they didn't tell you anything about the vector field F. I'm sure they wanted you to just leave it in this form. But in this case, you can say something because you can calculate the gradient of this magnitude function. Did anybody work that out? What's the gradient of the function that specifies the magnitude of a vector? Let's see, that would be, you can think of this as being, well, here, think of R itself as being the square root of x dotted with x. That's how you compute the magnitude of a vector, right? And so to compute the, I don't know, maybe that's not the best way to do this. I was trying to be slick about this. I'll do it in the unslick way. To get the gradient of f, you know you're supposed to take the partial of this r with respect to x, partial with respect to y, etc. But the magnitude function is just the square root of the sum of the squares of the components. And so in particular, as a function of x, it's just the square root of x squared plus all the other things. And so the derivative of that would be 1 over twice that square root times the derivative of what's inside, which would have been just 2x. And likewise, this one will be 2y over twice, oh, this is r again, and et cetera down the line. And if you cancel all the 2's, and factor out the scalar of r, what you discover is that you're just getting 1 over r times the vector x,
which is worth giving me a chance to remind you about something about the gradient. The gradient of a of a scalar field is a vector at each point. And about that vector, there's two things you might want to know, which is its magnitude and its direction. What do you guys remember about the direction of a gradient? Which way does the gradient point?
Towards the great direction of greatest increase.
Right, it points in the direction of greatest increase. And if you're talking about the function that measures the magnitude of a vector, well, to make that function increase as rapidly as possible, you should run directly away from the origin. So the direction that you should be running, the direction that the gradient vector should be pointing, is exactly in the direction of the vector x. Look, that's what we just found. It is, in fact, exactly the vector x divided by its magnitude. It is the unit vector pointing in the direction of the vector x. So that's just a little check that we've calculated things properly, but, and I was going to do it here with fancy symbols, but we get the right answer by writing it this way. This is what I believe they wanted you to insert in this spot when you select the right answer. I don't have the quest homework in front of me,
Yeah.
but I suspect that one of the answers, the right answer would be, it would just be 1 over r times x dotted with f plus r times the divergence of f. Is there an answer?
Yeah, yeah, one of the answer choice. That's one of the answer choices. Yes.
Good. There's a thumbs up. Oh wow, that looks really weird. Okay, thumbs up. Okay, cool. All right. Any other comments or questions that people want to ask about the existing homework, the one that had more questions about vector fields? I am leaving you guys a little high and dry on that. I know that. We could have spent more time on it, but it is kind of important for us to move on. By tradition, in 427L, when we come back from spring break, we switch gears. Instead of talking about differentiation, which is what we've been doing pretty much the whole first half of the semester, we now start talking about integration. And this is what's going to carry us through the rest of the semester. And I actually did give you guys a little bit of a thumbnail sketch of what integration was about, just, I think, on our very last day together before the break. So let me recap that part for you, because I need to make sure that you guys have this in your heads. You guys are used to seeing this symbol, and you probably have one of two reactions to that. You're either thinking, aha, we're going to talk about the area under a curve, or you think, aha, I'm going to anti-differentiate and stick in the endpoints. You need to let go of both of those. Neither one of those is really quite going to carry the day for you anymore. I can try to make reference to those as we go along, but I need you to get a different mental mindset about integration. For starters, the notation is going to be a little different. Anytime we use integrals, you'll see this symbol, and then there will be the name of a function or a description of a function. Of course, in our class, it's probably going to be a function of multiple variables. And then down here somewhere is going to be a set S on which that function is defined, some subset of the domain of the function f. And typically off to the right somewhere is well, basically it's just the right-hand bookend, like this is the left-hand bookend to tell you when you can stop talking about the function f. You're used to this. You know, your calculus teacher insisted that you write the dx at the end. It was very useful to have it there for the change of variables that you did, the u substitutions that you did in Calc 1, Calc 2. But we'll start to see some other notations. You will see things like a d sigma show up, or a dA, or, well, basically a lot of possibilities just with a little d in them. And I don't want to stress too much what those are for right now, but I will just start to indicate why we're switching notation when we do it. So if you ignore this part for a second, just focus on the function and the set that it's defined on. What you should be remembering from Calc 1 is neither of the two interpretations of an integral that I already mentioned. Instead, there was another one that I know your teachers mentioned. They said what you should have been thinking of is you take a sum of a bunch of products where you kept multiplying the values of the function f times the sizes of pieces of S. So that's where the two characters in this drama come together. It's values of the function and sizes of the pieces of the domain. And you multiply those together over and over again on each one of the pieces of the set S. So you're going to have to take the set S and split it up into pieces. But after you do that, you'll be able to compute such a product for every one of the pieces. You'll be evaluating the function f somewhere on each one of those pieces. And then you add them all up. You just take the sum of all of those products. And informally, that's how I will think of these integrals, although it wouldn't be calculus if I didn't also put in the word limit. So it's a limit as you keep chopping up the set S into finer and finer pieces. So this ultimately is what an integral really is. And if your Calc 1 teachers didn't stress this, then you got gypped, because this is the way you need to think about an integral. So let me show you how you should have thought of that when they wrote down integrals like this for you. Suppose that they asked you in Calc 1 to compute the integral from 3 to 5 of 4x dx. Yes, I know you can find an antiderivative and stick in the two endpoints. But what they should have said was, aha, you're going to take this function y equals 4x. You know the graph of that is a straight line through the origin with a slope of 4. You also know where the points 3 and 5 are on the real number line. And what they may have done but didn't emphasize is that it's not really the endpoints 3 and 5 that are important, but it's the whole interval that goes from 3 to 5. In fact, this notation, we won't really use this notation very much in this course. Instead, I'll be using a notation here where I need a set S in this lower right-hand corner of the integral sign. So I would write this as this much is the same, but this much changes into the interval that goes from 3 to 5. Now, what is this exactly? What they should have told you was, we're going to take this interval from 3 to 5 and split this up into a few parts. Maybe I have it going from 3 to 4, and then from 4 to 4.5, and then from 4.5 to 5. And then on every one of those parts, we choose a representative point. I'll call that point x1, the next one x2, and the next one x3. And I'm simply evaluating the function, this function right here, at each one of those 3 points. Now you know that when you evaluate the function at a particular value of x, that gives you what's supposed to be the y-coordinate in the graph. In other words, that's the height of this dot that's on the graph. So f of x1, the value of the function f at this point x1, that's the same as the height of this line segment. And f of x2 will be the height of this line segment, and f of x3 will be the height of this line segment. Now, when I talk about the sizes of the pieces of S, I broke S into 3 pieces. They're not all of the same size, but that's okay. This first one had a size of 1, meaning it was the width of 1. And these other 2 pieces each had a width of 1/2. But in each case, I multiply the width times the height to get the area of a rectangle. It's a rectangle that sticks out a little bit above the graph over here. It's a little under the graph over there, but it approximately shows the area of this portion of the region under the graph. And likewise, the width of the second interval times the value of the function at the second spot, that would give me the area of this second rectangle. And the third product represents the area of the third rectangle. And if you add those 3 products together, you get the sum of the areas of the 3 rectangles, which is approximately the area of the region that was under the graph and over the interval. That's a little trapezoid. Yes, I know you know how to compute the area of a trapezoid, but you're approximating it by adding together the areas of these rectangles. So that's what an integral really is. It's asking you to do exactly this kind of a computation, except you proceed to take a limit where the partition is replaced by finer and finer partitions that have more and more spots, more and more parts. It's, your teacher may have used a notation like this. They would have said you're going to take the limit of exactly this kind of a sum. You sum as I goes from 1 up to some big number n, where n stands for the number of parts that you've put into your partition. And what you're going to sum is the value of the function at some point within each one of those pieces. If you've got n pieces altogether, you'll have n points to choose. And you'll see in my picture, I chose the x's to be kind of in the middle of each of the 3 parts. They don't have to be in the middle. They can be on the left or the right, but somewhere they have to be a member of each one has to be a member of its own piece. And then you multiply that by the width of section number I. And that's a height, that's a width. You multiply those together to get the area of a rectangle. You add the areas of the rectangles together and you realize you've computed an area of a shape something like this. That's approximately the area of the region under the curve. It will become the area if you take more and more pieces. If your teachers wrote it this way, they were being a little sloppy, because it's not quite enough to say that I need you to take more and more pieces. You could imagine there's going to be some jerk who says, here, I'll show you. I'll divide this interval up into more and more pieces. First, I'll split it in half, and then I'll split this one in half, and then I'll split this one in half. And in so doing, they're creating more and more little pieces of the set S, but the partitions are not getting finer. This big chunk is never being made any smaller, right? As long as you're choosing your partition to have all the pieces have equal width, then in that case, it's fine to say, make the number of parts get bigger and bigger. But it turns out you don't need to make the portions equally large. You can go ahead and chop it up any way you want, as long as you take more and more parts to your partition and make the parts get smaller and smaller. So it turns out, at least for functions that we deal with in our class, we only deal with reasonably nice functions for which this limit will always exist. You always get the same value for the limit, no matter how you partition things up. And the value of that limit is exactly what this integral represents. So by all means, practice those skills of anti-differentiating, sticking in the endpoints, and so on. The fundamental theorem of calculus is still fundamental. It's still very useful, but it's not the meaning of what an integral really is. The meaning of the integral is this. It's the limit of the sum of products. And I will make that clear to you by doing a much harder integral, the kind that we do in this class, where we have functions of multiple variables. So here's my next example for you. I'd like you to compute the integral of this function. That's a 2. And my set S is going to be the unit disk, the disk of radius 1 centered at the origin. So you got to let go of this idea of area under a curve, because that doesn't help you interpret this. And there's no endpoints. I don't know what you would even try to do with endpoints. But still, we can compute this integral. First of all, let me say that I didn't put a dx over here. The right notation, I guess, would be to put dA. And the letter capital A in this case stands for the word area, because in this case, when I think about what the unit disk looks like, and I think of chopping it up into pieces, how would I measure the size of a piece? The way that you typically would measure the size of a piece of, let's say, a disk, would be to think about its area. So just in case that wasn't clear, I'm going to put the letters dA here to say this is going to stand for small amounts of area. Historically and informally, this symbol is actually an elongated S, which stands for sum, and this is a description of the function, and this stands for the little bit of area, which is really expressing in symbols the 3 things that I wrote over here. Anyway, forget about the history. That this is just asking you to take the unit disk, divide it into chunks, and measure the area of each chunk and multiply that by the value of this function somewhere, anywhere within that chunk. Now, when I say partition the disk, I mean, you could split it into little pie pieces, or you could split it into little rectangles, some of which would be not complete. They would have curly edges on the side. Or you could draw little jigsaw puzzles in here that, you know, would fit together and partition the set into other kinds of shapes. Just do whatever you need to do to split the unit disk up into a bunch of parts. Keeping in mind that I am going to ask you to, at least conceptually, you're going to split it up into finer and finer parts as you go. So these pie pieces, for example, I might ask you to start drawing a little polar coordinate grid in there, so it gets chopped up into finer pieces. Same thing with these little rectangles. You might split them into smaller rectangles. And then I'm going to ask you to go to each one of these sections and pick a point to stand in for that section, that piece. So these now are my points. I'll call them P1 and P2 and P3 and P4, but there's 1 point for each section, for each piece. And then I'm asking you now to compute the sum of the values of this function at these different points multiplied by the area of the piece that point is chosen from, piece number I. And of course, there's going to be a limit involved. We won't literally be taking a limit except to think about what we've done and then imagine doing it over and over again. But we'll take a limit as the pieces get smaller and smaller in area. Actually, there's a technicality. They need to actually get smaller and smaller in diameter, but don't worry about that. We're not actually going to be working to compute the limits. Now, in order to understand what it is that we've just computed, I think it would be helpful to think about the graph of this function. What's the graph of this function look like? Anybody know? You know, you could hit the space bar and
unit sphere. Yeah,
it's the units. Well, it's the top half of the unit sphere because we've got the square root sign. Square roots always mean positive square roots, but the graph is the set of points where the z coordinate is given by these values of the function. And I'm sure we've done this calculation before. When you square both sides and then move everything over to the left, then the top line says that z is positive, and the bottom line says that the point is on the unit sphere. So yeah, the graph of this function is in fact the unit sphere centered at the origin, the top half of the unit sphere centered at the origin in 3 space. So there's the graph. If I now try to redraw this picture that I was drawing down in the base of this hemisphere, I don't know how well I'm going to be able to do that, but there I drew some squares and puzzle piece back here and everything else. When I selected these points, I said, you're going to be asked to evaluate the function at these different points. These are points chosen down in the xy plane, x, y, see? And if I ask you to evaluate the function at that point, that means to take that point and go up to the graph and tell me what the z coordinate is when you hit the graph. But the z coordinate is the height of that dot. And so I'm asking you to tell me about the height of that one dot that somehow stands in for this portion of the disk. Take that height and multiply it by the area of that little region in the disk. So let me draw that a little off to the side. If I draw that sector of the circle, you still need to think about that being part of the xy plane. And then I say go up a certain height and multiply the height of that line segment times the area of this piece on the bottom. What you're going to get will be the area of this little, like a prism or a wedge of cheese. The volume of such a region is the height times the area on the bottom. That's the volume of this section of the, like a wedge of cheese, and that is kind of nestled in here in a portion of the sphere. Now, it doesn't rise quite as high as the sphere near the pointy part of the wedge, and it sticks out over the sphere on the back part of this wedge. So if I tried to draw the wedge, there would be a little region where it's exactly at the right height, but then parts of the wedge are too high to match up with the sphere, and parts of it are too low. But by and large, it's trying to more or less estimate what that portion of this solid hemisphere looks like. Same thing over here. If I take a point inside that little square and I ask you to go up that high and multiply that height times the area on the bottom of the square, well, now you're calculating the volume of a box. It's a box that happens to pierce the sphere exactly at that one point. Actually, it'll pierce the sphere exactly along a little arc. Inside of that arc, this little box is too low to touch the sphere. And on the other side of the arc, this box is sticking out. It's higher than the sphere. But generally speaking, it's matching the height of the sphere, at least in this portion of the disk. Now, if you do that for all these little portions of the disk, all the way we split up the disk, then you are going to start constructing little towers that stick out over each one of these little pieces. The tower will keep the same cross-section that the bottom does, but it'll rise up to a height. It'll rise up exactly as high as your one chosen point tells it to rise. That means that some of the tower will be lower than the hemisphere and some of it will be higher, but all in all, it's creating a picture that looks like a modern city underneath a bubble. So there's this big bubble, and inside of it is a bunch of towers all nestled together. Now I'm drawing my towers as if all the bottoms had been little rectangles, but you would see taller towers near the middle because the buildings would be trying to rise about as high as the bubble does over there. And then when you get out to here, the towers are a little smaller. And what the integral is asking you to compute is, it's the sum of the values of the function. Now those represent the heights of the buildings, and you're multiplying by the sizes, which now means areas. You're multiplying by the sizes of the footprint of the buildings. That's the size of the piece of the disk. And you add all of those things up, meaning that you're adding up the total volume of all of the buildings that are inside of the bubble. That's going to be approximately the same as the volume of the bubble itself. And in the limit, as the sizes of the pieces goes down to 0, what you'll discover is that that sum, the sum of the values, well, here, it's the values of the function at the different points times the sizes of the different pieces, that sum is going to get closer and closer to the actual volume of this bubble. When I say bubble, it's actually a solid hemisphere now. It's exactly half of a sphere of radius 1. The radius of the disk has now become the radius of the sphere. And so what you need is 1/2 times the volume of a sphere. As you may know, the volume of a sphere of radius r is 4/3 pi r cubed, where in our case r is equal to 1. And so I get a total of just 2/3 pi. So you have computed your first integral. That's the integral of this function of two variables integrated over this region in the xy plane. That's what an integral is. Obviously, this is not going to be a good way to compute it. In order for me to actually get a final answer, I had to have a formula for the volume of a hemisphere. And in general, I'm going to be asking you to compute integrals integrals of functions for which the volume doesn't have a pretty little formula that you already know. But we'll discuss next time how to make those calculations work. What we're going to need is something called Fubini's theorem. So I'll ask for questions, and then this will be where we stop for today. You guys need any clarification on this one example? All right, I see the chat bar has been glowing. Okay. I will take a look at the chats after I close this the Zoom meeting, but I will invite you to send your questions to me or to the TA. We'll try to get your question. Oh, a couple of hands went up. Yes. So Sahib, you have another question?
Yeah. So what happens if the set was not like if you're trying to measure the volume on a different set other than a unit disk?
Oh, then it would be a lot harder, wouldn't it? So we're going to do this in stages. I'll tell you what we're going to do. Fubini's theorem will help you handle the case where the set S is a rectangle that's lined up with the coordinate axes. It'll turn it into two Calc 1 type integrals. So that'll be straightforward. And then after we finish that, then we'll have a recipe to tell us how to handle a more general region. So it's a great question, but we're not ready to answer it yet.
All right.
And Nate, you have another question?
Just to clarify, you basically took half of the volume of the sphere, like the upper semicircle, because what you're trying to do is show us it's not just like the volume under that big surface. It's the sums of those areas as the sizes of those areas go to zero, and they just become points. Is that kind of what you're getting at?
Yeah, I don't want to say that those little regions become points, but yes, when these regions get smaller and smaller, they start, you know, to the naked eye, they start to look like an individual point. So you don't want to focus too much on the fact that I got an answer for you. To get an answer, I had to know how to calculate the volume of a bubble. What you should focus on is just that I got to this point. That if you take my recipe, my definition of what an integral really is, you'll see that in any of the cases like the ones I've just done, the integral will always be the volume of the region that lies under the graph, whatever the graph is, and at the same time over the set S. So that much will be true in every example, well, for the next week or two. Okay, so that'll be, getting further requires having a pretty formula for the volume of a pretty shape that happens to have a formula associated to it. In general, we'll be getting weird looking volumes, weird looking shapes, and so calculating the volume won't be something that you can just do because you have something memorized. So this would be about where we would stop in general. All right, and Eric, question.
Okay, so is it just for now, or are we only focusing on the functions that go from R2 into R1?
That'll be enough.
Will we do other types of functions?
We will definitely do other types of functions. For starters, we'll handle functions that go from R3 to R1. That'll be pretty much similar, but we'll also take the cases where you have a function of two variables, but the set S will just be a curve in the plane. And we'll be chopping that curve up into little bits of curves. And then the word size will have to mean length, arc length. So yes, we're going to be generalizing this to a lot of other types of situations. That's why I wanted to make sure that you guys had the general picture that an integral stands for the limit of the sum of products, because that's the one theme that's going to be constant in all the different types of applications that we do. It'll always be a limit of a sum of products. But the word size will change, the type of functions will change. Yeah, there's a lot more still to go.
So are we going to go over like a typical case of just from Rn into Rn or Rm into Rn and that kind of stuff?
No, well, here's what will happen is when you have a vector field, so that's a function that goes from Rn into Rn, then there's a new type of integration that we might want to do where we say things like, I want to walk around the outside of a surface and think of all those little arrows that are piercing my surface, and I want to somehow take into account how much of the flow is actually going through the surface as opposed to skirting along the side of it. So that's a dot product kind of a calculation. So you'll see that the vector fields will come in, but the only way that we're going to use them is we'll take a dot product of the vector field with something else, so that now we have we're just adding numbers, not vectors. So again, that's a good question, and there will be a form of that shows up. And I'll just tell you, your science and engineering people, this is not the mathematicians making this up. It was the scientists and the engineers that were very concerned about the flux of an electric field as it passes through a membrane and all that kind of stuff. So this has a lot of applications to the sciences and engineering. But you guys are asking great questions that are a little ahead of the game. We'll get these details down first. Got to start with Fubini's theorem. That'll be next time, and then we'll take it from there. I can see that I've held you guys way late, so how about if we stop here and we tune in again on Wednesday? Is that good? Thank you all for showing up today. We'll get a sense of how these classes are going to run. So tune in again on Wednesday and we'll take it again. Thank you.